All right, welcome to the module on acids and bases. So, before we begin, I want you to think about community and how in every conversation, someone's offering something of themselves, right? It could be in the form of advice, counsel, etc. And in this way, they're acting as an asset while someone else is receiving and integrating that offering, acting as a base. So, in the same way, in this module, we'll discover that atoms and molecules again engage in this same giving and receiving interaction that creates the chemistry that we see in community. So, some everyday applications or how we interact with acids and bases in our everyday lives. So, acids break something down by lending a proton or an H plus ion. And an example of an acidic environment is our stomach, right? Our stomach is really acidic so that it can break down the foods. Lemon juice is also very acidic. So it can actually cook raw fish in ceviche, which is really delicious, by the way. It can also clean hard water stains. Bases, right? They clean things up by accepting protons. So, an example of a basic environment is our blood. It's slightly alkaline to allow oxygen transport and enzyme function. There's soaps that are basic, which break down grime and grease because it actually accepts protons from that's found in the grime and grease that it's breaking down. And then baking soda, which is really basic, can absorb odors in spaces. This is why I don't know if it's common practice for you, but like growing up, we always had just a box of baking soda in our refrigerator, and that's to just absorb the odor and to keep the scent in the refrigerator fresh. So, we'll talk about two different ways that we define acids and bases. The first way is according to Bronsted Lowry definition, two people that came up with this definition, where they said an acid is any molecule that donates an H plus ion, and a base is anything that accepts an H plus ion, thereby forming a hydroxide ion. Or, I'm sorry, not, let me rephrase. So, a base is anything that can accept an H plus ion or a proton. So this is an example of a base, right? It's OH minus. This is why it's able to accept a proton if you think about it in forming water, for example. Okay, so here's an example of an acid-base reaction. So we have the base ammonia that is interacting with liquid water, which in this case, water is behaving as an acid. So the water is lending a proton or giving a proton to ammonia to form ammonium, NH4 plus. The base, right, accepted that proton to form ammonium. And so because water gave away a proton, it is left as a base or conjugate base as OH minus. So whenever an acid gives away a proton, what it's left with is it's what's called its conjugate base. And whenever a base accepts a proton, what it becomes is its conjugate acid. So up here at the top, we're showing the conjugate acid-base pair for both water and ammonia. So water as an acid is H2O. When it gives away a proton, it becomes OH minus, which is its conjugate base. And ammonia as a base, right, when it receives a proton, it becomes NH4 plus, which is its conjugate acid. So in acid-base chemistry, we start with an acid interacting with a base, and they form conjugate bases and acids. So let's talk about water, because water is interesting. It has this dual nature, and it's defined as amphiprotic because it can behave as both an acid and a base. So as an acid, it is actually donating a proton, and then it forms its conjugate base, which is a hydroxide ion. Water can also act as a base where it can receive a proton from some other molecule that's an acid, and in that case, it will form what's called a hydronium ion, H3O plus. It's giving Gemini energy, this dual nature of water. So here's an example of water as an acid. So we have this base, which is a pyridine ring, which is a base, and it is interacting with water as an acid. So water gives a proton to the pyridine ring, and it is left as its conjugate base, OH minus. And then the pyridine ring has an extra proton, and it becomes C5NH6 plus. Now, when we have a reaction between a base and water, it's called base ionization. Base ionization. And it's equilibrium constant. So when this reaction is in equilibrium, it is represented as K sub B. K sub B, because we have a base reacting with water. So we represent it as K sub B for base ionization. Now, when water is acting as a base, so here's an example of an acid, hydrofluoric acid. So this acid is going to lend its proton to water, and this is when we form this hydronium ion, H3O plus. And then we form hydrofluoric acid forms its conjugate base, which is a fluoride ion. So in this reaction, water is interacting with an acid, and so this type of reaction is called an acid ionization, and its equilibrium constant is represented as K sub A. So in acid-base chemistry, the equilibrium constant for these kinds of reactions are K sub A if we have an acid interacting with water, or K sub B if we have a base dissociating in water. All right, so I'm going to pause here.